But if I zoom in, and basically you will see that if I am patient enough, I zoom in enough, you see that, this is a parabola again. You will follow Hooke's law, okay? So that is actually really cool. So if I consider an arbitrary v of x, okay, we can do a Taylor expansion, okay, to this potential. So basically, v of x will be equal to v of 0 plus v prime 0 divided by 1 factorial times x plus v double prime 0 over 2 factorial x squared plus v triple prime 0 divided by 3 factorial x to the third plus infinite number of terms. And the v0 is the position of where you have minima potential. Okay, so that's actually where the equilibrium position is. Okay, so in my coordinate system. Okay, it's the same as the coordinate system I use for the solving the spring mass question. Okay, so if I calculate the force f of x will be equal to minus d dx v of x, and that will be equal to minus v prime v prime 0 minus v double prime 0 x minus 1 over 2 v double triple prime 0 x squared plus many other terms. Okay, since I have mentioned that v of 0, so v of 0 Vx. V of 0 is actually the position of the minima, right? Therefore, the prime of 0 will be equal to 0. Okay? Therefore, this term is gone. So what is actually left over is the remaining terms here. Okay? Now, if I assume that x is very small, what is going to happen? Anybody know when x is very small, what is going to happen? Anybody have the answer? Exactly. So when x is very small, he said that the higher order terms all become negligible. Okay? So that is actually correct. So when x is very small, then I only need to consider the leading order term. But how small is the question, right? How small is small? Actually, what you can do is to take a ratio between these two terms, right? So if you take the ratio, then basically you get a condition x v triple dot 0 should be much smaller than v double prime 0. So that is actually the condition which is required to satisfy so that we actually can ignore all the higher order terms. Then the whole question becomes f of x equal to minus v double prime 0 x. And that is actually Hooke's law. So you can see that, first of all, there's no Hooke's law in general. Secondly, Hooke's law is actually applicable almost everywhere when you have a well-behaved potential. And if you only perturb the system really slightly with very small amplitude, then it always works. So what I would like to say is that after we have done this exercise, you will see that actually we have solved all the possible systems, okay, which have a well-behaved potential. It has a minima. And if I have the amplitude small enough, then the system is going to do simple harmonic oscillation. Any questions? Okay. So no question, then we'll continue. So let's come back to this equation of motion. X double dot plus omega square x, this is equal to 0. There are two important properties of this linear equation of motion. Okay. The first one is that if x1 of t and x2 of t are both solutions, then x12, which is the superposition of the first and second solution, is also a solution. Okay. The second thing which is very interesting about this equation of motion is that there's a time translation invariance. So this means that if x of t is a solution, then xt prime equal to xt plus a is also a solution. Okay? So that is really cool, because that means if I change t equal to 0, okay, so I shift the 0 time, okay, the whole physics did not change. So this is actually because of the chain rule. So if you have this chain rule, dx t plus a dt, that is equal to d t plus a dt d x t prime dt prime evaluated at t prime equal to t plus a, and that is equal to dx t prime dt t prime equal to t plus a. So that means if I have changed the t equal to 0 to other place, okay, the whole equation of motion is still the same. On the other hand, if the k, or say the potential, is time dependent, then that may break this symmetry. Okay? Any questions? Okay, so before we take a few minute break, a 5-minute break, I would like to discuss further about this point, this linear and the nonlinear effect. So you can see that the force is actually linearly dependent on x, right? But what will happen if I increase x more? Something will happen. That means the higher order term should also be taken into account carefully. Okay? So that means the solution of this kind, x initial cosine omega t, will not work perfectly. Okay? In AO3, we only consider the linear term most of the time. But actually, I would like to make sure that everybody get this point. The higher order contribution is actually visible in our daily life. So that may actually give you a concrete example. So here I have two pendulums, okay? So I can now perturb this pendulum slightly, and you will see that, it goes back and forth, and following simple harmonic motion, okay? So if I have both things slightly oscillating and with small amplitude, what is going to happen is that both pendulums reach maxima amplitude at the same time. You can see that very clearly. Okay, I will need to do this carefully. You see that they always reach maxima at the same time when the amplitude is small. Why? That is because the higher order terms are not important. Okay? So now let's do an experiment. And now I go crazy. I make the amplitude very small, very large, so that I break that approximation. Okay? So let's see what happens. So now I release them. Okay. I release them at the same time and see what happens. You see that originally they are in phase. They are reaching maxima at the same time. But if we are patient enough, you see that now they are oscillating actually at different frequency. Okay? Originally, the solution, the omega, is really independent of the amplitude, right? So they should actually be oscillating at the same frequency. But clearly you can see here, when you increase the amplitude, then you need to consider also the nonlinear effect. Okay? So any questions before we take a 5-minute break? Okay, so if not, then we will take a 5-minute break and we come back here at 25. So welcome back, everybody. So we will continue the discussion of this equation of motion, x double dot plus omega square x equal to 0. Okay? So there are 3 possible ways to write the solution to this equation. So the first one, as I mentioned before, x of t equal to a cosine omega t plus b sine omega t. Right? So this is actually the functional form we have been using before. And we can actually also rewrite it in a different way. Okay? So x of t equal to a, capital A, cosine omega t plus phi. You may say, wait a second, you just promised me that this is the first one, the one is the one and only one solution in the universe which actually satisfy the equation of motion, right? Now you write another one. What is going on? Why, right? But actually they are the same, right? Okay? This is actually a cosine phi cosine omega t minus a sine phi sine omega t. Okay? So the good thing is that a and the phi are arbitrary constant, so that actually you can use 2 initial conditions to determine the arbitrary constant. So you can see that 1 and 2 are completely equivalent. Okay? So I hope that solves some of the questions, because people usually find it really confusing why we have different presentations of the solution. Okay, so there's a third one, which is actually much more fancier. Okay, the third one is that I have x of t. This is actually a real part of a, again the amplitude, exponential I omega t plus phi, where I is equal to square root of minus 1. Wait a second. We will say, Professor Lee, why are you writing such a horrible solution. Right? Really strange. But I will explain you why. Okay. So 3 is actually a mathematical trick. Okay? I'm not going to prove anything here because I'm a physicist. Okay? But I would like to share with you what I think is going on. I think 3 is actually just a mathematical trick from the math department. In principle, I can write it in an even more horrible way. X of t equal to the real part of A cosine omega t plus phi plus I f of t. And f of t is a real function. Okay, in principle, I can do that, right? It's even more horrible. Why is that? Because if I now have this function, I take a real part, and then I actually take the 2 out of this operation, right? So f of t is actually a real function. It can be something arbitrary. And I can now plot the locus of this function, this solution, on the complex plane. Okay? Now I'm plotting this solution on this complex plane. What is going to happen is that you are going to have that is actually what you are going to get. If I'm lucky, if this f of t is confined in some specific region. If I'm not lucky, then it goes out of the plane, and I couldn't see it, okay? Maybe go to the moon or something, okay? But if you are smart enough, and I'm sure you are, if I choose f of t equal to a sine omega t plus phi, can anybody tell me what is going to happen? Okay.
You go in a circle starting at the real axis to the right.
It becomes a circle. Very good. If I plot the locus again of this function, the real axis, imaginary axis, then you actually get the circle. Some miracle happened, right? If you choose the f of t correctly, wisely, okay, then you can actually turn all this mass into order, okay? Any questions? So I can now follow up about this. So now I have x of t. This is equal to the real part of a cosine omega t plus phi plus I a sine omega t plus phi. Okay? And just a reminder, exponential I theta is equal to cosine theta plus I sine theta. Therefore, I arrive this. This is a real part of a exponential I omega t plus phi. Okay? So if I do this really carefully, I look at this, the position of the point at a specific time. So now time is equal to t, okay? And this is the real axis, and this is the imaginary axis. So I have this circle here, okay? So at time equal to t, what you're getting is that x is actually, okay, before taking the real part, a exponential I omega t plus phi is actually here. And this vector actually shows the amplitude. Amplitude is A. And the angle between this vector pointing to the position of this function is omega t plus phi. Okay, so this is actually the angle between this vector and the real axis. Okay, so that's very cool, right? Why? Because now I understand why I call this omega angular velocity or angular frequency, right? Because the solution to the equation of motion, which we have actually derived before, okay, is actually the real part of the rotation in a complex plane. Okay, if you think about it, so that means now I see this particle going up and down. Okay, I see this particle going up and down. You can think about that it is as if there's an extra dimension which you couldn't see. Okay, actually this particle in the dimension we can see, and the extra dimension which is hidden is actually rotating. And what we see, the reality, is a projection to the real axis. You see? So in reality, this particle is actually rotating. Okay, if you add the imaginary extra dimension. Okay, so that is actually pretty cool, but purely artificial, right? So you can see that I can choose f of t to be a different function, and then this whole picture is different. But I also will create a lot of trouble because then the mathematics become complicated. I didn't get anything. But by choosing this functional form, you actually arrive at a very beautiful picture. Okay? Another thing which is very, very cool about this is that if I write this thing in this form, in the exponential functional form, okay, since we are dealing with differential equations, there's a very good property about exponential function. That is, it is actually a Phoenix function. Do you know what is a Phoenix? Phoenix is actually some kind of animal, a long-lived bird, which is cyclically regenerated or reborn. So basically, when this phoenix die, you will lay an egg in the fire, and you will reborn. Okay, this is actually the same as this function. I can do differentiation. Still an exponential function. I differentiate. Still exponential function. Right? So that is very nice because when we deal with differential equation, then you can actually remove all those dots and make them become just an exponential function. Okay? So it's really a very nice property. So the first property, which is very nice, is that it cannot be killed by differentiation. You will see how useful this is in the following lectures. Okay, the second thing which is really nice is that it has a very nice property. So basically, exponential I theta 1 times exponential I theta 2, and that will give you exponential I theta 1 plus theta 2, right? So what does that mean? That means if I have a solution in this form, A exponential I omega t plus phi, okay? and I do a time translation, t become t plus a, okay? Then this become a exponential I omega t plus a plus phi. So this means that time translation, okay, time translation in this notation is just a rotation in the complex plane. You see? So now t becomes t plus a, then you are actually just changing the angle between this vector and the x-axis. Okay? So as time goes on, what is going to happen is that this thing will go around and around and around, and the physics is always the same, no matter when do you start counting, and the translation is just a rotation in this plane. Any questions? Okay, so I think this is actually a basic slide. Just to remind you about Euler's formula. So basically, exponential I phi is equal to cosine phi plus I sine phi. And I think it will be useful, if you are not familiar with this, it is useful to actually review a little bit about exponential function, which will be very useful for this class. Okay, so I am running a bit faster today. So I think let's take a look at what we have learned today. We have analyzed the physics of a harmonic oscillator. So basically, we start by asking a really just a verbal question. Okay, what is going to happen to this mass on the table attached to a spring? And what we have learned is that we actually use mathematics. Basically, we translate all what we have learned about this mass into mathematics by first define a coordinate system. Okay, then I write everything in terms of that coordinate using that coordinate system. Then I use Newton's law to help us to solve this question. Okay, and we have analyzed the physics of this harmonic oscillator. And Hooke's law, we found that it actually not only works for this spring mass system, it also works for oscillations, all kinds of different small oscillations about a point of equilibrium. Okay, so basically, it's actually a universal solution, what we have been doing. And we have found that a complex exponential function is actually a beautiful way to present the solution to the equation of motion we have been studying. Okay? So everything is nice and good. However, life is hard because there are many, many things which actually we ignore in this example, okay? One apparent thing which we actually ignore is the drag force, right? So you can see that before I was actually making this pendulum oscillate back and forth, right? What is happening now? They are not oscillating anymore. Why? Why are they stopping? Right? Apparently something is missing, right? When I actually move this system, okay, if I turn off the air so that there's friction, then it doesn't really move, right? If I increase a bit the air so that it have some slight freedom, then actually you can see that it move a bit, then it stops, right? If I increase it some more, you can see that the amplitude becomes smaller and smaller. So in the following lecture, what we are going to do is to study how to actually include a drag force into the gain, And of course, using the same machinery which we have learned from here, and see if we can actually solve this problem.